Hello, everyone. On behalf of IBM Systems Magazine, I'd like to welcome you to our presentation. My name is Janine Donnelly. I am the Manager of Webinars for IBM Systems Magazine, and I will be the moderator for today's event. We will be holding a Q&A session at the end of the webinar. You may ask a question at any time during the event by entering it into the Q&A panel. If you experience technical difficulties during the webinar, please use the Q&A panel to alert us, and someone will assist you. You may download a PDF version of the slide deck by clicking on the drop-down menu labeled Event Resources on the left side of your screen. Today's webinar, The Top 2 Secrets for Modernizing Your Mainframe and Optimizing MLC Costs, is sponsored by BMC Software. Our featured speakers today are Reginald Stanfield and Jeremy Hamilton. Reginald is a technical software consultant for BMC's mainframe cost optimization suite of solutions. He has over 30 years of experience in the ZOS arena. He's spent the last 15 years assisting customers to maximize their use of BMC mainframe tools. Currently, he works with various customers to educate, consult, and implement cost management solutions. Jeremy is also a technical software consultant for the mainframe cost optimization suite. He has over 9 years' experience in the software industry, primarily in technical customer-facing roles. He started his career at IBM, where he worked with many large corporations and government agencies and wrote 3 IBM Red Books. Today, Reginald and Jeremy will discuss a proven methodology for lowering your MLC costs while increasing availability. With our introductions complete, Reginald, I'll turn the presentation over to you.
Thank you, Janine. I appreciate it. Good day, everyone. As Janine indicated, my name is Reginald Stanfield, and I am a principal software consultant with BMC. Joining me is Jeremy Hamilton, and we'll be spending a little bit of time today with you discussing ways that BMC has helped customers optimize and modernize their environment to take advantage and minimize their overall MLC cost in their environment. So we put together a brief agenda to kind of outline what we will be discussing during the presentation. We'll spend a little bit of time up front just so that everyone understands MLC, understanding the complexity of it, how is it calculated, what is this relationship to the rolling 4-hour average. And then we'll spend some time talking about how BMC has helped customers unlock some of the secrets related to MLC management, utilizing our intelligent capping solution, and we'll spend some time discussing that and how does that bring some savings to your environment from an MLC perspective. And then Jeremy will discuss using the subsystems as a service model and service-oriented approach to how the subsystems can actually be benefited from a mainframe perspective. And as Janine indicated, we'll have a slight Q&A session at the end of the presentation. So as we get started, we generally like to level set a little bit, talking about the mainframe budget overall. So if you think about the mainframe budget and how dollars are spent on a mainframe side of the house, you'll find from looking at this pie chart, you'll see that maybe there's 10% to other stuff like electrical, things of that nature. You have hardware costs. You have things around your ISVs, and then there's some people costs. And then you'll see that there are some costs around MLC. And generally, we ask our customers how significant is a priority is it regarding reducing the operating costs in their environment. And we have found that 86% generally say it's a pretty high priority for them. They want to get a handle on the costs of operating the mainframe environment. And one of the things that they look at, trying to actually get a handle around those costs, are the MLC costs, the cost of the software to run the environment, GOS, DB2, and so forth, because that generally makes up 30 to 35% of their overall budget. And we find that that budget is going up, or that cost is going up 4 to 7% year over year. And part of that increase not only is the cost of the software, but also the demands that are being imposed on the mainframe from a digital perspective, because the mainframe is now being part of that digital enterprise that says, I now have mobile workloads on the mainframe that's driving up that MLC cost. So we're going to stop for a second and do a brief polling question. And Megan, I'm going to turn it over to you so you can actually run this by our customer base.
Great.
I'm sorry,
No?
Janine, I apologize.
Quite all right. So as you can see, we have launched a survey. We're looking for your input to this question. How significant of a priority is reducing mainframe MLC costs in your organization? So choose the answer that best describes your situation and hit submit. We'll compile those responses and show the results to you, and we have a quorum here. I also want to let you know that later this week we'll be sending out a follow-up email with a link to the recording of today's webinar. So thank you. Some results are beginning to roll in. So give us just a moment while we compile the results. Okay, Reginald, I'm going to go ahead and send those results back out to the audience.
All right.
And you can go ahead and, did you want me to speak to those results?
No, I can speak to the results. So if we look at the results that just came in, we see that about 57% of you are saying that optimizing or reducing that MLC cost in your organization is relatively high in your environment, with another 18% saying it's critical and medium. So we do see that there is a need to reduce that overall MLC cost in your organization. So let's talk about how MLC cost is actually generated. How does it work? So let's talk about software pricing overall. Well, generally, when you used to get a box, IBM would charge you based on the full capacity of that box, saying that I want to use the box. I may not use all of the capacity on the box, but I want to actually be positioned in case I do. However, that caused you like a penalty. It puts you in a penalty because if you didn't use that full capacity, you will still charge for it. So based on that, subcapacity pricing came out. And with subcapacity pricing, you are charged based on the peak MSU usage versus being charged based on the full capacity of the box itself. So you don't necessarily get charged for the full box, but you get charged based on the MSU usage. However, one of the key things about that charge is the peak rolling 4-hour average. It plays a significant role in how you're charged as it relates to the MLC cost. So if you were like me and you thought thinking about subcapacity pricing and being charged based on the MSUs that you actually use, you would think that it would be a equation similar to this, that you're being charged on the MSU usage by the product. Those products in turn have a price associated with those MSUs. You multiply the MSUs used by those products by their price, and then you will get your bill. That would be your monthly bill as it relates to the use-based pricing. However, that is not how MLC billing is actually calculated. So let's spend a little bit of time talking about how MLC is actually calculated. So every hour, the machine generates how many MSUs is being consumed in an environment by the various components of that operating system. And every 4 hours of that result, you get a rolling 4-hour average, which is a sum of the 4 hours previous to it, and it's an average of those 4 hours. So in this case, you'll see what the rolling 4-hour average is for that particular environment. Well, over the month, that is done for every day of that month, which is 720 hours or so. So you collect a rolling 4-hour average every hour in that particular month. So when it's time to generate the bill, every hour has a rolling 4-hour average. When you're ready to generate the bill, it actually comes across and determines what is the peak rolling 4-hour average for that particular month. And we see in this case, hour 713 was the peak rolling 4-hour average, which is 704. So you would think I'll use that number to determine what will be my MSU cost based on hour 713, because that was the peak rolling 4-hour average. So if we looked at it from our usage perspective, you would think that my bill would look like this. I am at hour 713 at the peak hour of 704, and then I look at the MSUs consumed by each particular component of that. I look at ZOS, how many MSUs did ZOS use? How many MSUs did CICS use? And I would multiply that by the rate of the MSUs, and that would give me my total cost. In this case, that total cost is $127. However, the peak rolling 4-hour average is applied to every product that was running on that LPAR during that peak hour. So in this case, 704 gets attributed to every product that ran during that particular hour. So even though CICS may not have used 704, it was running during the peak, so therefore it is charged 704. So rather than your bill being $127, it's actually $300,000. So that's a little bit of difference between what you were thinking versus what you're actually charged. If you delve into that just a little bit more and start looking at the MSUs that are actually being consumed by each subsystem in that particular hour, you'll find that IMS is only using like 75% or 75 MSUs during that time, which translates to about 5% of the overall MSUs. However, since IMS is charged at a higher rate and is now being 704 MSUs, it makes up 29% of the overall bill, even though it's only being charged, only using 75 MSUs at the time, because that is because it was running during the peak, so therefore it gets charged 704. So if you start now looking at and start looking across multiple LPARs, because in this case I was only talking to one LPAR, but let's say that it was running across multiple LPARs. Now I have to worry about the aggregate peak for our average across all the LPARs. And so let's use two LPARs as an example. So each LPAR has its peak. However, the aggregate peak is the highest point of the rolling 4-hour average for both of the LBARs, the aggregate 4-hour rolling average. That is what will be charged because that's the CAC, and those two LPARs are running in that particular environment. So in this case, the peak is 1385. So, but let's say, for example, IMS didn't run on LPAR 2. All of the other subsystems, ZOS, CICS, DB2, and other miscellaneous MLC products run on both LPAR 1 and 2, so they will be charged $1385. Whereas IMS only ran on LPAR 1, and it will be charged the peak of that LPAR. So it will be charged at the 704 peak. So it will be charged 704. So that determines how my MLC bill gets generated based on what is running on what particular LPAR at either the aggregated peak for all the LPARs or the peak for the LPAR it is running on. So you can see over time as you start looking at this, this gets a little bit complicated. It gets a little bit overwhelming regarding what is my peak? What's the rolling 4-hour average? What products do I have running in what environment? particularly as your MLC expenses are about 30 to 35% of the mainframe budget. I need to find a way to control the overall rolling for our average peak, as well as controlling the subsystem MSUs in an effort to reduce the overall MLC cost. So before we proceed forward, we have another polling question that we'd like to put out there, and I'll turn it over to Janine to ask that question again.
All right, great, Reginald. This time, we're looking for your input to this question. What is your current level of capping today? So I won't go through the responses. You can see those there. Please make your selection and hit submit. Again, we'll be sharing these responses with you. And while we wait on those results, just a reminder, if you joined us late, that you can download a PDF version of the slide deck by clicking on the drop-down menu labeled Event Resources on the left side of your screen. And Reg, we're still going to pause just a moment here while we get some more results in. Okay, I'm going to go ahead and send those results out to the audience now.
All right. So looking at the results, we see about maybe 40% of you are using capping of some sort, maybe group capping, and then we have another 30% or so that don't want to necessarily cap because they're afraid of actually impacting SLAs or high importance work. And so that's kind of what we've seen in the marketplace as a whole. Because generally, people start capping in an effort to reduce those MLC costs. So how do I do that? How do I set a cap to reduce the overall MLC cost? The problem with setting a cap is you either, one, you can set it too high. If I set it too high, then it doesn't necessarily benefit me at all because my cap is too high. If I set it too low, then I can potentially impact my high importance work and affect SLAs as it pertains to my environment. And additionally, when you start talking about capping, is there a way to cap subsystems to reduce the overall MLC cost of a various subsystem by capping an environment? So what can I do to actually cap things but not affect my high importance work, my SLAs, but still get some MLC cost savings? So BMC has looked at that and came up with some loose solutions around that regarding what customers need from a capping solution perspective. Because if you look at it from the traditional perspective, things change, and things change relatively quickly. So I need something that can cap based on the environment and what's going on in the environment, yet don't harm my work. Make sure my work still gets through. Make sure my production LPAR gets the cycles it needs in order to get the work done. Yet, how can I reduce my overall MLC cost in the subsystems as well as my LPARs? To that end, BMC introduced Intelligent Capping for Z Enterprise, or ICAP. I may refer to it as ICAP as we go through the presentation. What ICAP does is allow you to implement a capping policy based on the work that's going on in the environment, yet still be cost aware from a subsystem perspective to make sure that you minimize the cost from a subsystem perspective as well as an overall LPAR perspective to reduce the MLC bill, yet still allowing the high importance work to get the MSUs it needs to complete and not impact SLAs, and actually make sure that your production LPARs get what they need and the test LPARs get what they need, but not at the expense of those production LPARs. We also allow you to know what you're going to do before you do it. So it gives you an opportunity to put ICAP in place and says, what would you do if you were capping? So it gives you an opportunity to tweak that and understand what will happen if you put ICAP in place and capping starts taking effect. So with ICAP, it is based on a policy, and that policy pretty much tells ICAP, what's my production LPAR? What's my test LPAR? Which ones have certain workload in it that I don't want to be capped at all? What happens when you reach a certain limit? How do you readjust and manage the MSUs across the environment? And to that end, if you look at the top right-hand side of the screen, you'll see what a traditional capping environment kind of looks like. So we have 3 LPARs in this case. So I have an LPAR 1, 2, and 3. If I have a defined cap set on those LPARs, when that cap is reached or you get hit from a rolling for our average perspective, workload will be delayed. It doesn't care if it's going to be high importance work, low importance work, it will be delayed. However, if LPAR 2 and 3 had headroom as it do in this case, well, their work is going on just fine, but it's a large percentage of low importance work. And you'll see in this example, the rolling for our average is 811 MSUs, but my high importance work is being delayed or capped on LPAR 1. With ICAP, I'm able to set an MSU limit, define a priority for my LPAR 1 that says I don't want him capped. I want him to get the MSUs he needs. LPAR 2 and 3, because they have a larger percentage of low importance work, take MSUs from those LPARs, give them to LPAR 1, allow him to get the benefit of additional MSUs, complete its work, yet lower my overall MSU consumption, because I dropped my MSUs to 650 versus 811, yet still allowing my high importance production work to actually proceed forward. Now, one of the things that you have to be concerned with, particularly as it relates to ICAP, because ICAP is manipulating the MSUs and reallocating them based on the needs of the LPARs. So in some cases, in this case, this example, I have an MSU limit set for 500. So I'm saying, in the sense, in general, I was using maybe 600 MSUs. By setting an MSU limit of 500, I save 100 MSUs from a ZOS perspective. However, since ICAP is reallocating MSUs, it inadvertently caused LPAR 2, where IMS is running, to now get its MSUs raised up. So now in this example, IMS LPAR is running 410 MSUs. So I've increased the number of MSUs on IMS by 100 MSUs. So I save some MSUs from a ZOS perspective, but I cause the IMS bill to go up. However, ICAP is aware of that from a cost perspective. So ICAP understands what's the cost of running a subsystem on a particular LPAR. So there's a cost awareness feature within ICAP. So that cost awareness tells ICAP that I can't allow certain LPARs to exceed a certain MSU limit because of the costs associated with the subsystems running in that environment. So ICAP will manage to that cost limit to ensure that that particular subsystem does not exceed a particular MSU limit. So that way I'm keeping my costs down on my LPARs, keeping the cost down from a ZOS perspective, and keeping the cost down as well from my subsystems, because ICAP is cost aware based on the policy that is defined to it. So let's expound that just a little bit further. So now I have certain LPARs. So let's say I have multiple LPARs running multiple different subsystems. I may have LPARs that are dedicated to IMS, multiple LPARs. I may have a service bureau that that I use and manage. ICAP allows you to build what we call sub-policies. So I have a policy within a policy. Again, with the idea of minimizing the number of MSUs that's being consumed by those LPARs So I can actually keep those LPARs within a certain MSU limit, reducing their costs. They get the benefit of the manipulation of the MSUs based on the workload importance, and I still get some cost savings overall because of that overall MSU limit. So this is an example of using a sub-policy based using IMS. So I have 6 LPARs in my KEC, and there are 500 MSUs that's being shared by the 6 LPARs in the KEC. However, I have a sub-policy for 2 of the LPARs because they run IMS, and I want IMS to be managed to 200 MSUs. ICAP can manage those 2 LPARs separately than the overall KEC itself. So now those 2 LPARs that run IMS is limited to 200 MSUs. They get the benefit of MSU reallocation based on the need of those 2 LPARs, and these 2 other LPARs have access to the entire MSU limit of 500. So I'm able to, 1, reduce the overall ZOS costs as well as reduce the overall IMS costs because I'm keeping it within a certain MSU limit. I can combine that with the cost limit as well to actually reduce the overall cost of that particular subsystem. And this is just another example, so I can push that a little further. So let's say I have certain business units that I want to manage as well and keep the costs down on certain business units. In addition to the subsystems, I can group business units together and says, I only want these business units to utilize 200 MSUs. I want another business unit to have 500. And again, I'm reducing their costs in the environment, reducing my ZOS costs, reducing the cost for that particular business unit. If they're running various subsystems in that environment, I reduce the cost of those subsystems running in that environment as well. So ICAP is dynamic and makes adjustments on the fly and understands what is going on from a workload perspective, what is going on from a priority perspective for the LPARs, with an overall need of reducing the overall MSUs being consumed with the objective of reducing the overall MLC bill. So to summarize it, ICAP uses policies to determine what it's going to do and when it's going to do it, and manage the defined capacities across the entire KEC and across the entire WLM workloads. I'm able to reduce the capacity being utilized because ICAP understands what is going on from an environmental perspective, what LPARs are more important than others. I'm able to reduce the overall MSU consumption, reducing my overall MLC bill, and I'm still able to manage the rolling 4-hour average. Remember that peak rolling 4-hour average determines what will be my MLC cost. So I'm able to reduce that using ICAP, and also reduce the subsystem cost as well by using the cost limitation feature of ICAP as well. And so with that, I'll turn it over to my colleague Jeremy, who will talk about some things around subsystems and how to optimize some of the subsystems.
Thank you, Reginald. Janine, we have a polling question.
Great, yes we do. Okay folks, we are looking for your input on this question. What is your current level of capping today? We actually made it applicable so you could choose both A and B. So check those if they both apply. Otherwise, whatever applies to your situation, make your choice and hit submit. Also, just a reminder, we will be having a Q&A session at the end of the material. So feel free to submit your question anytime. We'll reserve your questions for the end and hope that we can get to all of them. And Jeremy, I'm going to give it a few more seconds here.
Okay.
Results are starting to come in. And I think if I just wait for one more update, they're tabulating in the background. Okay, I'm going to go ahead and send these results out, Jeremy.
Okay. Well, as you can see from the results, how your company might benefit from optimizing subsystem placement. Many of you are not sure. Hello, my name is Jeremy Hamilton, Senior BMC Software Consultant, and I will be presenting you the second secret to optimizing and modernizing your MLC. That not sure answer is pretty standard. When's the last time you had to think about how your mainframe environment was structured? That's where the LPARs are, the subsystems that are running on them, and the workloads that are driving their MLC costs. Now, obviously, the structure must fulfill the business needs, but is it optimized? Now, when you're thinking about the optimization, two factors quickly emerge. Cost, are you getting the most out of the MSUs you're paying for? And availability, can you efficiently meet the availability goals that your business requires? Now, earlier in this session, Reginald described how MLC is calculated, which is a matrix of LPARs and subsystems that are running on them, and that combined peak 4-hour rolling average for each. So from a cost standpoint, the IBM subcapacity pricing model doesn't make it that easy to get your money's worth out of every MSU you're charged for. In fact, the subcapacity pricing is inherently not even close to utilization-based pricing. So you're not getting exactly what you're using. If you think about availability, the effects of outages, maintenance, IPLs, etc., are enough to worry even the most robust of systems, especially as the demand for uptime has increased and software updates have become more frequent. Cost optimization and availability enhancement don't always go hand in hand, but this is one of those very few areas that the mainframe can actually learn from its distributed cousins. For many years in the distributed world, they've utilized the service-oriented architecture, or SOA. SOA provides an architectural model that's helped organizations optimize their infrastructure from both a cost savings and availability standpoint. And SOA is the basis for our second secret. That's a subsystem service model for mainframe infrastructures. With the subsystem service model, we can now extend the benefits of SOA, the agility, the availability, and cost savings onto the mainframe platform. And BMC has simplified the transition to this model by adding the subsystem optimizer for Z Enterprise. So let's start by defining what SOA is, and then I'll show you how the subsystem service model extends it. It all starts with a service. And a service is simply the action of doing work for someone else or supplying a need to others. In order for a service to exist, there must be a service provider, and that's the one providing the service, and a service consumer is the one that's requesting the service. The service consumer sends a request over to the service provider, and the provider will process the request and send the response back to fulfill it. The consumer and provider can be isolated logically or physically, but they can run on the same platform or they can run on separate platforms and be built in a way that optimizes how they perform their function. Now, a single service isn't very exciting, but when you have a collection of services, and they can be orchestrated together to create many wonderfully efficient and resilient composite applications. Now, you may be wondering why I've been using Legos in the presentation so far, and it all goes back to when I was in grad school. A professor of mine described SOA by comparing the differences between blocks and Legos. Blocks are solid and sturdy, but they're also heavy, have a fixed function, and easily knocked over by change. This represents those applications in your environment that perform a single fixed business function. The Legos, on the other hand, represent service-oriented architecture. They're light, easily integrated, and can be quickly combined into various shapes and sizes to fit a need. This is similar to how the SOA services come together into composite applications. In the SOA world, there's always been this black box Lego, and that's your mainframe LPARs. Now, traditionally, mainframe LPARs and the applications running on them have been approached as only a service provider to the composite SOA applications that are talking to the outside world. However, when you take a look what's actually going on in the LPAR itself, you can see that there are service consumers and service providers. On the service consumer side, we have your MQs, your CICS, and your IMS transaction managers. And on the service provider side, we have your database managers, your DB2s, and your IMS. So since we have service consumers and service providers within each LPAR, then why not bring that SOA approach over to the mainframe? And that's exactly what we've done with the subsystem service model. The key concept of this model is, like SOA on the distributed world, is isolating the service consumers from the service providers, specifically focusing on the isolation of mainframe transaction managers to LPARs that are away from the database managers. This has a lot of benefits, especially from a cost savings and enhanced availability standpoint, and we'll explore those in just a second. This approach can be done today without any additional software using standard IBM APIs, but that could potentially require a large amount of change to your applications and infrastructure. BMC offers the Subsystem Optimizer for Z Enterprise to enable your environment for this subsystem service model. It functions by intercepting the data requests coming in from the service-consuming transaction managers and routing those requests over to a remote LPAR where the service-providing database manager will reside. All this while being transparent to the business applications and without any application code changes. So let's take a look at a couple of examples. Here on the left-hand side, you see two LPARs, each running the four major subsystems. Now, these LPARs combined would contribute to the MLC cost for the subsystems that are running on them, in this case, all four. Additionally, those LPARs would have to be maintained with all those products in mind. So if you're making an update to CACS, DB2, or IMS, you have to worry about MQ and everything else running on that LPAR. On the right, we have the subsystem service model. Here we've isolated each subsystem onto a respective LPAR. Those LPARs can now be optimized for running their individual subsystem. So the subsystem cost simply becomes a function of what's running on that LPAR alone instead of across all the different LPARs. And the complexity of the LPAR was reduced to a single subsystem and ZOS, of course. Now, let's talk about cost savings. Here's our two LPARs again. This time, they're only running CACS and DB2. In this model, those two LPARs combined, their peak 4-hour rolling average combined, would be how much you paid for CACS and DB2, and when they calculate MLC cost. The graphic down below in red shows us what our CACS MSU utilization is for those two LPARs. And we can see that it's about 80% of what it is being charged at. With the subsystem service model, we can isolate CACS onto its own LPAR, leaving the database managers where they originally started on its original LPAR, and now CACS will be charged for what's running on its LPAR and is very much closer to its true utilization. This produces a dramatic cost savings for CACS, and the number of NSUs that is charged for is reduced down to the single LPAR. This could potentially produce cost savings on the DB2 side as well, depending on where the new rolling 4-hour average is calculated. But we know that cost is only one factor. The other one that I asked you to take into consideration is availability. So in the before example here, we have two LPARs. And on LPAR B, if the whole LPAR goes down for some reason, or if DB2 that's running on that LPAR goes down, maybe you're applying maintenance to that DB2, then the entire transaction set that's pointed at LPAR B must wait until it's brought back up in order to fulfill those transactions. With the subsystem service model, if LPAR B or the DB2s that are running there go down for some reason, you can designate a different DB2 that's already up and running to complete the transactions. And in our case, our LPAR A has a DB2A running there, and we can route those data requests over to the new LPAR to go ahead and complete while we're working on LPAR B. If you're using the BMC Subsystem Optimizer for Z Enterprise, you can designate a primary, secondary, even a third option for a database manager to fulfill those database requests. Now, these designations can be specific, can be generic, in a DB2 group, or even across CPC, as long as the LPARs where the database manager is running is in the same sysplex. And when you take a step back and let's think about maintenance. Now, I recently read that DB2 is moving to a continuous release cadence. This means that keeping up with the latest and greatest enhancements will require a greater number of maintenance windows. And we've seen that type of maintenance release cycle increasing over the entire mainframe software stack, and especially in the last few years, in order to stay ahead of those technology advances that are coming so rapidly. The subsystem service model will provide two key benefits here. One, you have the needed redundancy to stay available while staying current. And two, LPAR simplicity, or fewer subsystems and products to worry about on each individual LPAR when you're applying maintenance. So just to recap, the subsystem service model extends the SOA approach over to the mainframe. In the past, mainframe LPARs have been treated by SOA as simply a black box service provider, and it was not able to take advantage of the cost savings and availability benefits from the approach. The service-consuming transaction managers and the service-providing database managers were housed on the same LPAR, producing higher cost per subsystem and adding additional LPAR complexity. With the subsystem service model, we address this gap, allowing the mainframe shops to realize those cost savings through subsystem isolation, provide the redundancy options for availability, and reduce the complexity of the individual subsystems for maintenance. Now, all this can be achieved today simply, effectively, and transparent to your business without any application changes with the BMC Subsystem Optimizer for Z Enterprise. So we've covered a lot of ground today, provided you with the top 2 secrets for optimizing and modernizing MLC. We started with understanding MLC, how it's calculated, the role of the rolling 4-hour average, and the inherent complexity that, of understanding where your mainframe dollar is actually going. We then discussed how intelligent capping can help you safely manage the rolling 4-hour average for cost savings while maintaining your SLAs. And lastly, we took a look at the subsystem service model, which extends the benefits of service-oriented architecture onto the mainframe for cost savings and availability enhancements. With that, Janine, I will turn it back to you to answer any questions that may have come in.
All right, great, Jeremy. Yes, we do have some questions, so let's get started. How much CPU overhead does ICAP add?
I'll take that, Janine. This is Reginald. The overhead from an ICAP perspective is negligible at best because ICAP is really just monitoring the system like it would any other monitor would do. It only does work when it needs to. So the overhead from an ICAP perspective is barely noticeable because it's not really doing anything until he needs to do something. Hope that answers the question.
Got it. Okay. Next question, do I have to add LPARs to use Subsystem Optimizer?
I'll take that. This is Jeremy. No, you don't have to add LPARs at all. In fact, again, the key concept of Subsystem Optimizer and the Subsystem Service Model is just isolating the transaction manager from the database manager. So within your environment, we just need to understand where you would like to put the subsystems in order to get the optimization.
Okay. Does ICAP require me to use main view?
No, ICAP does not require you to use main view, and I'll add a little bit of background regarding that. If you're familiar with the main view monitors, ICAP utilizes the infrastructure of main view to do its communication. So if you have main view, there's some synergy and some connectivity between ICAP and main view. However, you do not need to have main view installed to utilize the capabilities of ICAP. The ICAP will take advantage of some of the inherent strengths of main view, such as setting alarms, setting alerts, doing things around automation, providing a GUI interface into ICAP. So it takes the inherent strengths of main view and extends them to ICAP, but it does not require the use of main view itself.
Okay. Next question. How can the 4-hour rolling average be managed when all LPARs in a CPC are close to cap level at the same time? Does ICAP identify any low priority workload that could be deferred?
ICAP, when he looks across the environment, one, you set an MSU limit. So that MSU limit is the number that ICAP will manage to and make sure that that rolling 4-hour average doesn't exceed that particular MSU limit. If everybody is close to their cap level, ICAP looks across the environment for the percentage of low importance work that's running in the environment. It does not look at the particular workload that will be. It can't delay from a WLM perspective. It's not going to change that. But it will look at which LPARs that I'm managing has a larger percent of low importance work. And that is the LPAR that will experience a delay or a cap first, because ICAP will base its information on the priority of the LPARs, and the LPAR that has the largest percentage of high importance work will get the MSUs. So there is a possibility that some LPAR could potentially be capped. And generally the way we set it up is to allow a test or a QA or sysprog image to experience that delay, because I don't want that delay to be extended to my production LPARs and actually impact my SLAs. So we identify the percentage of low importance work that is running in an LPAR to determine who will experience the delays from a capping perspective.
Great. Next question, is Subsystem Optimizer moving my transaction?
I'll take that one. Actually, no. So what we do is when a transaction comes in, even if it's on the same LPAR, it's going to make a data request to DB2. What we do is we intercept that data request and route it to the remote LPAR where the database manager is running. So we're not actually moving a transaction. We're just routing the data request over to where the database manager is running and then routing the response back to complete the transaction.
Okay. Next one, does ICAP have a simulation capability?
Yes, Janine, it does. What ICAP has 3 different modes that we can say it runs in. So generally, ICAP, when you first implement it, runs in what we call an observe mode. And the observe mode allows ICAP to get a better understanding of the environment, what's the rolling 4-hour average, how are the LPARs prioritized, which one's production, which one's test, and what percentage of low importance work runs in those LPARs. The next mode is what we call message mode. So it simulates what ICAP would do if it was actually managing the environment. So get a message that says, I would have raised the MSUs on one LPAR, lowered them on another. So it gives you an opportunity to tweak your policy that says, I want to change that a little bit. I want to set this as a priority 1 LPAR. I want to not cap this LPAR. I may have my MSU limit set high or low. So it gives you an opportunity to see what ICAP would do before you actually put the capping in place. The third option is manage mode. And in manage mode, ICAP will actually manage the environment and starts manipulating the MSUs in the various environments that it would manage. So there are 3 simulation modes from an ICAP perspective. There's observe, where he's just taking a look and see what's going on. Message, that will tell you what he would do if he was actually managing the environment. And then finally, the actual management of the environment itself, which is manage mode.
Okay, great. Seeing no more questions, I want to thank everyone for attending today's webinar, and I especially want to thank Reginald and Jeremy for sharing their expertise with us today. Again, later this week, we'll be sending out a link to the recording of today's webinar, as well as some other links to valuable BMC resources. Don't forget to check out the ones that are listed here on this slide. Those links should be live if you'd like to check them out right now. That concludes our webinar. Thanks again, everyone, and have a great day.